Right, let's jump straight in. Have you ever actually stopped to think about what happens inside your devices? Every single time you tap a screen, send a quick message, or ask your virtual assistant a question, you're kicking off an incredibly complex, lightning-fast relay race of information. Today, we're going to follow that data step by step, tracing its fascinating journey from raw binary code all the way up to complex artificial intelligence. Here is our roadmap for today. We're going to break this down into 6 essential chapters: decoding and compressing, safe transmission, hardware basics, system software, cyber threats, and finally, automation and AI. Let's get started.
Chapter 1, Decoding and Compressing Data.
Okay, so every piece of media you interact with starts out as raw, uncompressed binary data. But to store and share it efficiently, we really rely on compression. And there are 2 main ways to do this. On one side, we've got lossy compression. Think MP3s for audio or JPEGs for your photos. This method actually permanently removes data. It cleverly relies on the limits of human perception, literally throwing out sound frequencies or tiny color changes that our eyes and ears can't even pick up anyway. Then on the flip side, we have lossless compression, like run-length encoding, or RLE. Lossless methods encode repeating patterns without losing a single detail from the original file. For example, instead of saving 20 black pixels one by one, RLE just records a quick code for 20 black pixels. When you decompress it, bam, the file is exactly as it was originally created.
Chapter 2, Safe Data Transmission.
Once our data is compressed and packed up, it has to travel across global networks, bouncing from router to router. But think about this for a second. How does the computer actually know if a file arrived safely? What if bits were scrambled along the way because of electrical interference? I mean, if you send a file and just one single 1 flips to a 0, the whole thing could become totally unreadable. So how do our devices catch these invisible errors?
This is where some truly ingenious error-checking protocols come in. If an error is detected, protocols like ARQ kick into gear. ARQ stands for Automatic Repeat Request. It's basically a relentless safety net. It works by having the receiving device send back a positive acknowledgement if the data arrives intact, or a negative one if it spots an error. But what if the data just gets lost entirely in the void? Well, ARQ handles that using a timeout mechanism. The sending device waits a predetermined amount of time, and if it hears absolutely nothing back, it automatically demands the data be sent again.
Now, data can actually travel in a few different ways down these channels. Think of simplex transmission like a traditional radio broadcast or a one-way street. Data flows in one direction only. Half duplex allows two-way communication, but not at the exact same time. It's basically like using a walkie-talkie where you have to say over before the other person can start talking. And finally, full duplex allows data to travel in both directions simultaneously, much like a regular telephone call or your high-speed internet connection. Before we move on to the actual physical hardware, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Chapter 3, Hardware and Storage Basics. Let's look at the physical realm.
We've talked a lot about data flowing across abstract networks, but this is the actual silicon that does the heavy lifting. The central processing unit, the CPU, breaks down into components with very specific jobs. You've got the control unit, which ensures everything is synchronized perfectly. The core is the part putting in the actual heavy processing work. And then there's cache memory. This is so crucial. It provides vital, temporary storage space right next to the processor for your most frequently used data and instructions. It basically stops the CPU from constantly having to wait around for slower memory systems to catch up.
Speaking of memory, when we talk about primary memory, we really have to distinguish between RAM and ROM. RAM, or random access memory, dictates your operational speed. It's the workspace where your currently running programs live, but it is volatile, meaning the second you lose power, it forgets absolutely everything. ROM, or read-only memory, is the exact opposite. It's non-volatile and permanent. Its main job is to securely hold the essential startup instructions, like your BIOS, so your computer actually knows how to wake up when you hit the power button.
And how do we actually input data into these physical machines? Usually touchscreens, but they definitely aren't all created equal. Capacitive screens, which is what you likely have on your smartphone, allow for multi-touch features like pinching and zooming, and they look incredibly clear. Infrared screens also allow multi-touch, but they can be a bit sensitive to moisture. Then you have resistive screens. Now these sacrifice multi-touch entirely and can scratch easily, but they are incredibly resistant to water and dust. That makes them perfect for harsh environments or outdoor ATMs.
Chapter 4, Systems Software Essentials.
Here's the truth. Hardware is just a very expensive paperweight without the software needed to bridge human intent with binary execution. To actually talk to hardware, we use translators. Programmers write in high-level languages that make sense to us, but CPUs only speak binary. So compilers translate the whole program in one go to create a final executable file. It takes a bit longer up front, but the final program runs super fast. Interpreters, on the other hand, translate the code line by line while the program is actually running. They don't give you a standalone file, but they are absolutely fantastic for debugging because you can spot errors and tweak the code directly on the fly.
To write this modern software, programmers live inside an integrated development environment, or an IDE. It's a game changer because it bundles all the essential tools into one single application. Instead of using a bunch of separate programs to write, translate, and test your code, an IDE gives you a code editor, a built-in translator, and a runtime environment all in one place. It even uses real-time error diagnostics and autocompletion to catch typos before they happen, drastically speeding up development. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never missed our weekly exam strategy sessions.
Chapter 5, Cybersecurity Threats and Defenses. With our software running and data flowing, we enter the most dangerous part of the whole journey. The digital landscape is crawling with malicious actors creating all sorts of malware. We tend to use the word virus for everything, but a true virus is a very specific code that replicates itself by attaching to host programs. Trojans are completely different. They disguise themselves as legitimate software to trick you into installing them. And then you have ransomware, probably the most feared right now. It ruthlessly encrypts all the data on your computer, literally holding your own files hostage until you pay a fee to the attacker. Aside from malware, attackers use social engineering and network tricks, and it is absolutely vital to know the difference between phishing and farming. Phishing is a classic con game. You get an email that looks totally legitimate, maybe pretending to be your bank, trying to trick you into actively clicking a dangerous link. Farming is way more insidious. Malicious code is installed on your computer or a server, and it actually changes the IP address of a website. That means you could type the correct, perfectly legitimate web address into your browser, take no risky action at all, and still be automatically redirected to a highly convincing fake site designed to steal your passwords. Chapter 6, Automation, Robotics, and AI.
So, what happens when we use all this secure process data to let machines make complex decisions for us? We get automated systems. Whether it's a smart thermostat or a massive factory robot, they all follow a continuous, rapid loop. First, sensors read analog data from the real world, like temperature or light. That analog data goes through an analog-to-digital converter, or ADC, so the microprocessor can actually read it. The microprocessor compares this new digital data to its pre-programmed rules. If things are out of range, it takes action. That digital command passes through a digital-to-analog converter, a DAC, which triggers a physical actuator, like spinning a motor or opening a valve, to adjust the environment. If you look at the logic, it builds into a perpetual flowchart. The system is constantly checking conditions, making a rapid yes or no decision based on the data, adjusting if it needs to, and then immediately looping right back to check the sensors again. This closed loop lets processes run optimally 24/7, entirely removing the need for human monitoring. It's safer, it's faster, and it's infinitely more consistent. But what if we want these systems to do more than just follow a rigid flowchart? That's where we turn to artificial intelligence. Now, AI is the broad, overarching goal of making machines simulate human thinking. Machine learning, on the other hand, is a very specific subset of that. It's the practice of feeding machines massive amounts of past data, so the algorithms can literally train themselves. Instead of a programmer having to manually write an explicit rule for every single possible scenario, the machine learns to recognize patterns and solve entirely new problems autonomously. When this technology peaks in specific fields, we get what are known as expert systems. These are incredible applications designed to replicate high-level human decision-making. Think diagnosing medical conditions or finding underground oil reserves. They work by combining a massive knowledge base of facts gathered from actual human experts, an inference engine that applies logic to those facts, and a strict rules base. Through a simple user interface, a total non-expert can ask the system a question and get expert-level problem-solving advice back. We've seen how data transforms from basic binary, compresses to travel across networks, processes through hardware, powers complex software, and defends against cyber threats, all culminating in these autonomous learning systems. But it definitely leaves us with a big question. As we transition to a fully automated future driven by machine learning and expert systems, what is the ultimate value of human intuition? It's a fascinating thought, and one we're going to have to figure out as the journey of data continues. Students who implement these strategies see major improvements. Subscribe to our YouTube channel, Ace the Exams at Ace the Exams IGCSE, to excel in your Cambridge examinations. Subscribe right now to Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.